Hello guys, let's talk about normal depth boundary conditional in HEC-RAS, about friction slope. I think it's a very important question. It's my first real-time translate from Russia into English, and I think I will be a little bit slowpoke. Don't be angry. Although you can see on screen a dam bridge model, I think a dam bridge model can show you how important it will be a boundary condition normal depth. We have a water storage and dam about 100 meters high, and we have purple line, it's normal depth boundary conditional. Let's go run animation to see what happened. It's not difficult to imagine what will be happened when after dam bridge. We will have a very big wave with a steep slope with high velocity, and this wave will be running to the downstream cross section. Okay, let's push stop and we will see a profile plot of normal depth cross section. Look at these values, 15 fucking meters. It's very great value. And let's go make a time series plot of this cross section. What will we see? 50 meters deep. How quickly? Very quickly. What it mean? It means what the beginning of the wave, the slope of the beginning is very steep. We have big steep wave, and if we going to unsteady flow data and choose the boundary conditional, what we will see? Usually we can see the digital in the friction slope, just a slope of our terrain, no more. Yes, it's working when you have calm, quiet river, subcritical flow. But when you have supercritical flow, like a dam bridge wave, it doesn't work. The next step I will recall what is it energy of cross section. And the first attribute of cross-section energy is critical depth. What is it, critical depth? Critical depth is the theoretical depth who divide the flow into the supercritical flow and subcritical flow. Subcritical flow, it's very slow, like a river, non-turbulence, common river regime. And supercritical, it's like very steep mountain creeks. Very turbulence, it have high velocity, and it have a lot of скоростной напор. How to translate? Этот самый кинетическая энергия, kinetic energy. Let's go to draw a profile plot. This is first is supercritical flow. Look at water surface. It's very turbulence. It's very shape maybe. And this is blue. It's subcritical flow. Very slow, non-turbulence regime, like a common regime of over rivers. And what we must remember, what critical depth? It's a theoretical depth when energy of cross-section is minimal. Do you remember what is it energy of cross-section? It's a sum of кинетическая и potential and kinetic energies. In this parabola we have a minimum. What? It's a red point. In x we have v квадрат на 2g, это блядь, кинетическая энергия, kinetic energy, and potential is h, it's high of, deep of our cross-sectional. And the critical depth is a red line. It's the theoretical depth when this point of energy is minimal. And when we have a supercritical flow, we have most kinetic energy, and subcritical blue line, we have very big potential energy. The next attribute is slope. We have three types of slope. At first, let's go to draw a profile plot of river. Alpha 1, it's a slope of river bed. Blue line, it's a water surface. It will be angle of slope alpha 2, it's a slope of water surface, no more. And let's go draw a green line, it will be energy line. Let's choose green, okay. And with alpha 3 will be slope of energy line. You need understand what these three types of slopes are different. Sometimes these three slopes are similar, but not all time. Look at screen. I prepare a small model in a Storm sanitary analysis. We have a трапециидальный channel. Я не знаю, как будет трапециидальный. And we have a water race in the middle part. You can see that very steep slope. And when we run on animation, we will see how to flows going into this channel, and the green line, it's an energy line. Look, this green energy line is highest on the water surface line. Okay, I have to explain what's happened in this unsteady 1D Saint-Venant unsteady flow model. Look, I need to say what this model is the exact model of real physics. But we can imagine and we can draw our theoretical water surface. No, at first part I draw it's red, it's normal flow, subcritical maybe. Here at this point we have some like a wear effect, like a wear, okay, understand? And after that we have a very quick, very steep slope part. It's a water race, maybe. It's have a very high velocity, supercritical flow, and in the next point here we have very big velocity, the kinematic energy, and it will become a hydraulic jump. Here, Obana jump, and after that we became a normal flow after hydraulic jump. When the end, it's the way of outfall. It's not important for us now. This model is not so exact, but it's sufficient enough from engineering tasks or problems. Okay, and what we will see in a green line. Our green energy line show us the velocity of flows. Here not so big, here the most big values in this part, and after hydraulic jump it's became to aware. It's going to aware. It's not important for us. This part is not important in our problem now. and we need to understand what with the slope of green line not all time can be like a slope of riverbed or slope of water surface. And now I want to show you how it works in a differential boundary value equation. Imagine what this cable is a differential equation. It have flexibility, liquidity, I don't know what else, as you wish. And my fingers, it's a boundary condition. For example, left it's upstream conditional and right it's downstream conditional. And when we change boundary conditional, we will become different integral curves, like S, like inversional of S. You can have like just a line, or like omega, like a mountain. And you need to know when you change a boundary condition, you will change the solve the determinational inside your model. And sometimes it will be correct or sometimes not. And your final model depends on the boundary conditional. It will be correct or not. It's very important to understand when you use a finite difference method in mathematics. When you use finite volume method or something else. Before setting a task in HEC-RAS, you need imagine the real flow in your head. Let's go draw the profile plot of our dam bridge. It's the first black line, it's bed slope with its dam. Okay. The real slope is no matter in this drawing. It's like a children picture. And at first time step we will have after at first second of dam bridge T1 we will have a very big wave. And the second time step T2 we will have the wave who are going downstream. You will see in this picture. In the next time step T3 we will have the next wave, and you can say what this wave it's not it's have a reduction, it's have not so big flow, maximum flow. And the next wave in time step 4 T4 we will have very long but without maximum of flows of our wave. And let's choose the first wave in time step 1 and the last wave in time step 4. What we must know first, what the volume of the wave 1, what this volume I drawing it in red, I draw, and volume of the first wave when was dam disaster, it's the same volume. Yes, it's equation of как там conservant mass, да? It's the same, okay. The second, the maximum of flows are different because the flow in time step 4 will be a reduction. And the third, look at a gradient of the slope of water surface in the first wave, alpha, green. Look at the picture. And the slope of water surface at the downstream. We can see what the alpha 2 more similar with a riverbed slope. But the water slope near the dam is so fucking steep. So fucking steep. Let's go to see a time step plot of downstream cross section. We will see what the highest dip of 15 meters became in a very small time. It means what the slope of water surface are very steep too, and the energy gradient very steep. We must understand what in this place near the downstream cross section the water surface slope and energy slope is not similar with terrain surface slope. We're different things, fucking. And it's incorrect to become the terrain slope, choose and going into a normal depth conditional and write the terrain slope here. And what we can do? We can do two things. The first thing, I think the most correct and most right. We need move a section, cross section downstream as far as we can. If we can in analytical equations have a solve how far from our disaster dam became a reduction of our wave. 1 kilometers to 10 kilometers or 100 kilometers, it's no matter. We can at first answering these questions. When you understand what the spreading, reducting of the wave occurs after 100 kilometers or 10 kilometers, you can move your cross section down using, for example, satellite SRTM surface. If we cannot move the downstream cross section, we can do second thing. It's not so correct in my opinion, but it works. You can change the friction slope like an average slope of water surface of your wave. You can assume this slope in interesting cross section by analytical equations. But you need to understand what this slope will change from time to time. And you can use just an average value of friction slope in your normal depth boundary condition window. I think this step is not so correct like first when we are moving, when we had moving our downstream cross section as far as we can to a terrain. But it's sometimes it works.